All right, so last thing we'll finish up with is we're going to look at section 7.2, but just the first part of it. Okay, so it's very short. It's only like 6 or 7 slides, but there's one thing from section 6.5 that we didn't get to finish, and that has to do with a pattern of something in the quadrants. Okay, we already looked at this formula for the quadrants. Okay? If you have a coordinate, okay, and you want to find the angle for that coordinate, okay, the first step is to find the reference angle. Okay? If you're in quadrant 1, the reference angle is the answer. There's nothing else you have to do. But if you're in quadrant 2, 3, or 4, the reference angle itself is not the answer. Okay? If you're in quadrant 2, you subtract the reference angle from 180. If you're in quadrant 3, you do 180 plus the reference angle. And then if you're in quadrant 4, it's 360 minus the reference angle.
So that's to find the inverse?
Yep, and to find the reference angle, this is what you do. You do the inverse sine and take the absolute value. Okay? Or when you're finding the reference angle, if you just draw it out, okay, so say -2, 3. When you make your triangle, if you just consider that as 2 and that is 3, you won't have to take the absolute value. Okay? Technically, it is a -2, but if you just think of it as 2, you wouldn't have to take the absolute value. And I think that's how I did it yesterday. I said this is 2 and this is 3. All right? So I made the numbers positive to start. All right, so any questions on those formulas? All right, so let's look at a angle that's in quadrant 3. All right, so somebody give me a coordinate that's in quadrant, call this example 5A and 5B. So what would be a coordinate in quadrant 3?
-4, -6.
-6. Okay, so what I want to do here is the same directions as the previous one. Find theta. Okay, so this point is on the terminal side. Find the angle. Okay, so let's draw it out. You don't need a grid, but it does look a little nicer on the grid. So left 4, down 6. 4, 6. That point is on the terminal side. Okay, so there's my terminal side. Where's the initial side if they don't tell me where to put it? Positive x-axis. So there's your initial side, and this is the angle you're finding. All the way around that section. Okay. Any questions on that? Okay, so what we're really going to do to find this is really making a triangle right there. We're going to find this angle. Okay? Let's see. From here to here. That's the angle we're going to find. And then we just have to know how far is it from here all the way to here? 180. So if this is 180 and you want to get to here, what would you do with 180 and this angle? You would just add them. And that's exactly the formula that I showed you in quadrant 3. 180 plus your reference angle. Okay? That's why you do that. Right? So we'll find this reference angle first. All right, so the top side, and you can make your triangle any size you want, right? You can make it larger, you can make it smaller. It doesn't matter. I think it's easier if I just draw it right there. Okay, I'm going to draw a little smaller version. And how long is this side? 4, and this side? 6. And if you think of it as +4 and +6, even though they are negatives, you don't have to worry about taking the absolute value because you already made the numbers positive. Okay? So now we're going to do inverse sine. But what side am I missing? I'm missing the hypotenuse. Okay? And sine has hypotenuse. So sine is opposite, I know that one, over hypotenuse. I don't know that. Okay, so we find the hypotenuse using the Pythagorean theorem. What's 6 squared?
36.
And what's 4 squared?
16.
And what's 36 plus 16?
48.
52. Okay? Now, if you can reduce that, I mean, sometimes we want to, but that's not the final answer. So don't worry about reducing it. We're going to type this in, and we're going to get a decimal anyway. So, and I don't care that the root is in the bottom. If you were leaving that as a final answer, I would care. Okay, but we're not going to leave that. So now, how do you get rid of sine? Inverse sine. So we're going to take the inverse sine of what's on the left, and we're going to take the inverse sine of what's on the right. And when I type that in, that's going to give me that angle from there to there. Okay? It's not the whole angle. I've got to add that to 180 to get that. Okay, but it's that small angle right there. All right, let's do it in degrees. So we've got inverse sine of 6 over square root 52. Okay, so that angle is 56.31 degrees. Now, what did we add that to get the angle in the third quadrant? 180. Take that angle, add 180, and this entire angle that I just drew is 236.31 degrees. That's the answer. So you can find the angle for a coordinate in any quadrant just following those formulas I gave you. Now, all these formulas assume you're in degrees. What would you use in place of 180 if you were doing radians? Yeah, you would use pi, and what about 360? 2 pi. Okay, so keep that in mind too. If you're doing radians, you're not using 180. It's pi. All right, so any questions on that? So, kind of a special case that can happen is the quadrantal angles. Okay, those are the angles that land right on the quadrants. 0, 90, 180, 270. If you get a coordinate that lands on one of these 4 spots, you just have to memorize what it is. Because you can't really draw a triangle out of this point. Okay, there's no hypotenuse. Okay, if I had a point over here, then yeah, I can draw the hypotenuse like that. I can draw that side, and there's my triangle. Okay. But if I try to do that here, it's like, okay, I draw my hypotenuse, and you can't really draw anything else. Okay? So if you have a coordinate that's here, 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 or here, you just have to memorize this diagram. And what would all of these coordinates have in common? How does a coordinate land on the axis? 4, 6, or negative 4, negative 6. That definitely doesn't land on an axis. Has to have a what? Has to have a 0 in it. Okay? Any coordinate that has a 0 in it somewhere will land on an axis. Okay? Like this one. This is 0, comma, could be 3, or 0, 4. This coordinate right here, that's like 5, comma, 0. Right? So anytime you have a 0 in a coordinate, your answer is always going to be one of those 4 numbers. Right? So any questions on that? All right, so how about, let's do this one. If that point was on the terminal side of an angle, how big would my angle be? 180. Yep. How about if I had, if that coordinate, I gotta have a 0. Let's go like this. If that coordinate was on the terminal side, how much is that? That's 270. Okay, so figuring out the angle when the coordinate has a 0 is a lot easier. All right, and the last thing I'm going to show you in this section is a diagram to determine where trig functions are positive and negative. It all depends on the quadrant you're in, so this is important to know. Let's start with sine. Okay, somebody give me some angles in quadrant 1. Any angle. 45. Okay, I got a positive answer. Okay, somebody give me another angle in quadrant 1. 3. Okay, another one. 30. So what do you notice about all of them? They're all coming out what?
Positive.
Positive, and they will. Any angle that you take the sine of between 0 and 90 comes out positive. Give me some angles in quadrant 2.
270.
No.
130.
130. Quadrant 2 is between 90 and 180. Okay, so that comes out positive. Let's try another one. 110. That comes out positive. They're going to keep coming out positive. So actually, anything in quadrant 2, the sine is also positive. Give me an angle that's in quadrant 3.
265.
265. I got a negative. Okay. Another one would be 200. I get a negative. So it looks like the pattern, if you take the sine of anything in quadrant 3, it's negative. How about an angle in quadrant 4? 280. Yep. Anything between 270 and 360, that's also negative. 350, that's also negative. So there's 2 quadrants where sine is positive, 1 and 2, and there's 2 where it's negative, 3 and 4. Now we can look at that with each trig function. With cosine, there's 2 quadrants where cosine comes out positive all the time, and there's 2 where it comes out negative, but it's not the same as sine. And that also happens with tangent. 2 quadrants where it's positive, 2 where it's negative, and that's different from sine and cosine. So this diagram basically tells you where the trig functions come out positive and where they come out negative. If you are in quadrant 1, all the trig functions come out positive. I showed you the sine does, but all of them actually do. Okay, so A stands for all. If you're in quadrant 2, okay, the only trig function that comes out positive in quadrant 2 is the sine. That's it. So if you give me an angle between 90 and 180, and I take the sine of it, I guarantee you it will come out positive. If I take the cosine of it, it's going to be negative. If I take the tangent of it, it's going to be negative. It doesn't tell me what it is. I'd have to take it in to see. But I can at least tell you if it's positive or negative. If you're in quadrant 3, the only function that comes out positive in quadrant 3 is tangent. And if you're in quadrant 4, the only trig function that comes out positive there is cosine. Right, so that's a diagram to figure out where trig functions are positive or negative. Okay, so you just have to remember ASTC. Sometimes people try to remember it by all students take calculus. Right, because you're all going to take calculus after this. Right? Or all calculus teachers smell. You could do it that way. I don't know. Come up with a way to remember it somehow. But ASTC. All right. So, any questions on that? So this doesn't describe the secant, the cosecant, and the cotangent, or does it? Because I didn't mention those other two.
It does indirectly, kind of.
It does indirectly, because when you flip a number, right, that's the other three, when you flip. Does flipping something change the sign of it?
No.
Like if you had 2/3 and you flip it. 2/3 started out positive, you flip it, it's still positive. So if the tangent is positive in quadrant 3, what else is positive? The cotangent. If the sine is positive in quadrant 2, then what else is positive? The cosecant. Yeah. So the reciprocals are obviously follow the same rules. Okay? So you only need to know that. So any questions on that? All right, so that's the last thing in 6.5 we didn't get to. But this diagram, this idea is going to come up a lot in chapter 7 and 8. All right. So what I might do is give you a problem and say, okay, here's a value. Tell me where the sine would be positive. Well, there's two answers. Sine is positive in quadrant 1 and quadrant 2. So I'm going to ask for both answers. Okay. Or I might say something like, here's an angle. Tell me where the tangent would be positive. Well, there's an answer somewhere in quadrant 1 and somewhere in quadrant 3. You have to give both answers. All right? So just make sure you have that written down or remember that somehow. All right. So that finishes up 6.5. There wasn't really much left. And now we're going to take a look at just the first part of section 7.2, which is pretty short. And this section is all about inverse trig functions. Okay? Some of the things you already know how to do, like type them in. We're going to look at some pictures of them, but we're not going to do any sketching by hand. Okay? All the sketching will be on the calculator. All right, so first thing I just kind of want people to understand, and this is true not just for inverse trig, but true for any inverse function. If you want to know what the inverse of a function is visually, it's a reflection. It's a reflection over the line y equals x. Right, so for example, let me draw something that's an inverse function, but not a trig function. Okay, I'm going to graph x squared. I'm going to try. And I'm going to graph the inverse of squaring. Okay, what's the inverse of squaring? Square rooting. So I'm going to graph these two pictures, and I'm going to show you how they are a mirror image of each other over the line y equals x. These are both in quadrant 1, so no need to focus on negative values. Okay, there's x squared. There's the square root of x. And you know what? Let me put in the line y equals x as a dotted line so you can see the mirror image. And actually, I don't need it to be dotted. It's fine. All right. So if we take a look at that, that black line is y equals x. And can people see how the blue line has been flipped over right onto the red? Okay, if you were to take that blue line and almost like pretend like this was a piece of paper. If you folded it right on the black line, the blue would land right on top of the red. Okay? So that they're mirror images of each other over the line y equals x. Okay? And that's also true for sine and inverse sine. If you graph sine and you graph inverse sine, they will be mirror images, okay, of each other over the line y equals x. Now, in order for a function to have an inverse, it has to pass a certain test, okay, called the horizontal line test, not the vertical line test. The vertical line test tells you if something is a function. The horizontal line test tells you if something has an inverse. So the horizontal line test basically says that if you draw a function, put a horizontal line anywhere you want, as long as the horizontal line only hits at one time, then your function has an inverse. All right, so now I want to think about the graph of sine. What does sine look like?
Wave.
It's a wave. It looks kind of like this. If I put a horizontal line, is it going to hit the graph more than once?
Yes.
Yes. It hits it infinitely many times. So that's a problem, because I just said for a function to have an inverse, it has to pass the horizontal line test. Well, sine just failed it. Okay, it hit it more than once. But we have an inverse sine button on the calculator, so there must be some way around that. So here's the graph of sine. Okay. The way around that is, instead of thinking of sine forever, we're just going to look at a small section of it that does pass the horizontal line test. Right? So I'm going to kind of block everything out, and I'm just going to leave like a window of it open. And I want to look at that. And let's look at that section. Okay. That's the section from 0, 90, 180. That's 0 to 180. If I put a horizontal line in that section, would it hit it more than once?
Oh, yeah. Yeah.
I don't know if I can. Yeah, I know. Does it hit more than once?
Yep.
Yeah. So looking at that section between 0 and 180 doesn't really help. Let's drag it back this way a little bit. Okay. What if we look at that section? It's a little off, but it's pretty close.
Yeah, it's good.
Yeah. No matter where I put a horizontal line here, in that section, it's only going to hit one time. Okay? Which means if we're willing to just look at that small section, then we can do inverse sine. We can't look at the whole thing. We've got to look at that small window that I'm showing you right here. Okay? Does anybody have a guess what that's between? It's negative something.
Negative 90 and positive 90.
It's between negative 90 and positive 90. So when we look at inverse sine, what we're going to do is we're going to restrict the domain of the original to just say we're between negative 90 and 90. If we don't, then when you do inverse sine, you would get multiple answers. You'd get an answer every time that horizontal line crosses the graph. And we don't want that. When we do inverse sine, we want one answer. So if we all agree, we're going to give the answer between negative 90 and 90. We will all always get one answer. Okay? If we said, well, let's give the answer between 0 and 180, that's a problem. Because now I might ask different people for the answer, and some people might give me this one, some people might give me that one. Okay? As long as I go between negative 90 and 90, that won't happen. Everybody will always get the same answer when they do inverse sine. And that's how your calculator does it as well. Okay? Because the calculator has to decide, well, which answer should I give? There's infinitely many, right? If you think of sine forever. But the calculator is going to narrow it down and say, I'm only going to give the answer between negative 90 and 90. Okay? So that's how we can use inverse functions with sine. Any questions on that? Right? So now let's I want to look at this, and this is the domain and range of inverse sine. Okay, I wrote it in words and then I wrote the symbol. Does anybody recognize this from anything? This negative 1 to 1? Think about the regular sine function. What was negative 1 to 1 in the regular sine function? That was the range. Remember when we drew sine? This is the regular sine function. What's the highest that it went?
-1.
And what's the lowest that it went? -1. So in the regular sine function, the range was -1 to 1. Now, -1 to 1 turned into the what here? It turned into the domain. So what happens when you look at a function and its inverse? The domain and range flip. Okay. the domain of the original becomes the range in the inverse. Okay? And the range in the original becomes the domain in the inverse. Okay? So I said here, we're going to restrict the domain of the original function to be negative 90 to 90. So if I restrict the domain on the original, that becomes the range on my inverse. Okay? So domain and range switch places when you're talking about inverses. Right, so let's graph inverse sine on the calculator and see if that's what happens. Okay, so I'm going to type in inverse sine of just x. Get rid of weird parentheses. Okay, and I said that it's only going to go between negative 1 and 1 on the domain, so let's go negative 2 to 2. Okay, and the range is going to be negative, that's about 1.57. That's 3.14 divided by 2. So let's go negative 2 to 2 on the range. Okay, and you will see a picture of inverse sine. If I set my calculator in radians.
It's just going to be the same thing except on the other axis, right? As sine.
Yeah, it's going to look, oh, you'll see what it looks like. That's what inverse sine looks like. Yep, and that's it.
Are you really zoomed in?
Nope, that's the whole picture.
Oh,
There's nothing else to see. That's it.
no, I know, but that's like out.
Oh, I'm zoomed in a little bit. Yeah, I'm zoomed like negative 2 to 2 and negative 2 to 2. If you do zoom 6, like negative 10 to 10, it's going to look really tiny.
Yeah.
Now, if I wanted it in degrees, I wouldn't do negative pi over 2 to pi over 2. I could do negative what to what?
90.
Negative 90 to 90. That's why it didn't look right the first time I graphed it, because I was in degrees. But that's what inverse sine looks like. Right, now inverse cosine. Let's think of the original cosine function. Starts here, comes down, and it keeps repeating. What's the highest value that it hits? 1? Oops. And what's the lowest? And what do you call that in the original? Negative 1 to 1 is it's the range. So if negative 1 to 1 is the range, what do you think that becomes in the inverse? It becomes the domain. Okay, so in the inverse, the domain is negative 1 to 1. And this time, we can't use negative pi over 2 to pi over 2 like I did right here. That doesn't work. Okay, what we end up using this time is 0 to pi. I'm not going to draw it, but if you draw it out like I did here and set up this little transparent window thing, you can drag it and you can see why this works. Okay? But just trust me that it does. Right? And if you want to graph inverse cosine, we can look at that one. This time, I don't need to set my domain any different, but my range has to go from 0 to 3.14. So what would I have to adjust here to go a little higher on the range?
Your y.
The y max. Let's just put it up at 4. Okay, so I'm graphing inverse sine and inverse cosine. Both, you're going to see both. That's the one I just drew. And that's inverse cosine in red. Okay, so it's up a little bit higher, but it still has that same kind of curve to it, pretty much. It's almost like you could just copy and paste that curve and kind of flip it and move it up, and it'd look pretty much the same. All right, and now tangent. When we drew tangent, we had these vertical asymptotes. And how high and low does the graph of tangent go? Yeah, remember it goes up, looks like this. It goes up infinitely high and it goes down forever. So what is that when you're talking about how high and low something goes? That's the range. So the range here is negative infinity to infinity. That range is going to turn into the what in the inverse? Domain. So now the domain is negative infinity to infinity. And in the original tangent function, what kind of asymptotes are these? Vertical or horizontal? They're vertical. So in the inverse, vertical is going to turn into, it's going to turn into horizontal. So now I'll show you a graph of inverse tangent. Okay, this one looks a little different. And that's because tangent looks a little different. Sine and cosine kind of look the same. Tangent's totally different. Okay, so let's graph inverse tangent. I'm going to get rid of the other two because it's going to look confusing if I put too many at once. So domain is negative infinity to infinity. So I would say negative 10 to 10. It's probably enough. If you need more, you can put more. And that's about negative 1.57. So I'm going to go negative 2 to 2 on the range. So negative 2 to 2. Okay, and there's your graph of inverse tangent. Okay, hopefully you can kind of see that there are horizontal asymptotes. There's one at, I'll put it as pi over 2, and negative pi over 2. Okay, so if I put those two lines in, you should see the blue curve will never reach them. It'll get very close. But that's where inverse tangent is kind of trapped between those two values. So I just wanted you to kind of see what those inverse functions look like. We're not going to be doing any sketching of them by hand, just on the calculator. So any questions on that? All right. So I'm going to look at a few different properties for inverse sine, inverse cosine, and inverse tangent. Some of these we've already used yesterday. Okay, but I'm just going to get a little bit more specific about them. So what this first property is saying is that if you put inverse sine right next to regular sine, these two things are going to cancel each other out. And the only thing that's left is whatever you started with. Okay, it's kind of like taking a number like 5 and doing plus 2 and then minus 2. Well, if you do something to it and then you undo it, you just get back exactly what you started with. The only catch is you have to start with something between these two angles, negative 90 and positive 90, okay, if you were doing it in degrees. All right, so somebody give me an angle between negative 90 and positive 90. 15. So I'm going to type in this formula, and I'm going to use 15. The inverse sine of the sine of 15. What should I get when I hit enter? 15. And I do. You cancel out. Okay, give me another angle between negative 90 and 90. 45. So I hit enter, and I get back what I started with. They cancel out. Now, give me an angle that is not between negative 90 and 90. 180. So when I typed that in, I didn't get back what I started with. Okay? So this formula will only work for angles between negative 90 and 90. Now, yesterday when we did right triangle trig, we did this. We practiced taking the inverse sine of each side to cancel it out. But I didn't tell you about this. How come I didn't have to tell you that the angle has to be between negative 90 and 90? We weren't working in other quadrants. Right? When you do right triangle trig, think of your angles. What's the biggest that either one of these angles could ever be?
60.
Can be bigger than 60. Yeah, like 89.9, right? You can't, 0.999 repeating, because you've already used up 90. So we were never working with angles bigger than 90 anyway, and we certainly weren't working with negatives, so I didn't need to tell you that. But if you wanted to just use this formula in general, okay, forget about working with just triangles, you'd have to use it with angles between negative 90 and 90. And the difference between formula 1A and 1B, all you're doing is you're switching the order. Now you put the inverse on the inside, you put the regular sign on the outside. Well, these two things, they also cancel each other out. And whatever you're left with is what you started with. But what does it say you have to start with? Something between what and what? Negative 1 and 1. All right, so let's try it. Somebody give me a number between negative 1 and 1. 0? So when I hit enter, what should I get?
0.
Yeah, and I do. Okay, they cancel each other out. Give me one more. A half?
Yeah.
0.5? I get 0.5. Okay, so these will always cancel each other out between negative 1 and 1. Somebody give me a number that's not between negative 1 and 1. 2. This time, you don't even get a different number back. You don't even get a number back. Okay? 2 is outside the domain of inverse sine. Okay? Look at this middle part, inverse sine of 2. You're trying to plug in an x value of 2. If you look at inverse sine, what did I say the domain had to be between? It doesn't even exist at 2. You can't go that high. That's why we got an error. It has to be between negative 1 and 1. Okay. So any questions on that one? Right. And there's two formulas like that for inverse cosine and inverse tangent. Okay. These formulas would be something that you would probably want to put on a reference sheet rather than try to memorize them. Okay, but they're very simple formulas, just as long as you know the conditions when they work. Right, now you guys did this one yesterday too. We took the inverse cosine of both sides of an equation to cancel out cosine and get x by itself. But it only works between 0 and pi. But again, I didn't tell you this yesterday. What is pi in degrees? So it's 180 degrees and 0 degrees. How come I didn't need to tell you this condition yesterday? Yeah, we were only working with angles that were between like 0.1 and 89.9. Right? It couldn't get any bigger or smaller than that. So the angles were automatically always in this condition. We never worked with ones that weren't. Okay, in formula 2b, it's kind of like 1b. They just switch the inverse and the regular cosine. And these two formulas will cancel out. This will cancel that as long as you pick a value between 1 and negative 1. Okay, and if you're wondering, well, why does it have to be between 1 and negative 1? Yeah, look at inverse cosine. Inverse cosine doesn't exist past 1. It can't. Right? It only exists between negative 1 and 1. Okay, and the last one is for tangent. And it's all the same stuff I already said. Now, 3b is a little different on the condition. Think about inverse tangent. How far to the left and right does inverse tangent go? Infinite. So this formula doesn't really have a restriction. This formula will always work because inverse tangent goes left and right forever. It looks kind of like this. It's got that curve in the middle. All right, so that's something you really have to pay attention to when you're doing right triangle trig, because these conditions are automatically always true. But in general, what I could do is ask you a question like, is the inverse sine of the sine of 12 degrees. Is that equal to 12 degrees? Okay, so what you could do is check, right? Inverse is on the outside, regular is on the inside. That's this one. Inverse is on the outside, regular is on the inside. So in order for that to be true, you had to give me an angle between negative 90 and 90. That's the condition for that formula. Is that angle between negative 90 and 90?
Yeah.
Yeah. So then you could say, yes, this is true. Or if it was a yes-no question, you could say, yes, that is. Right? So you might see a true-false kind of question with that stuff. Okay. Anything on that? All right, so transformations. When you do a transformation with an inverse trig function, it works exactly the same as every transformation we've done all year. Nothing is different. And really, the only thing I'm going to ask you to figure out when we transform functions is I want to know the domain and range. Okay? Because all of these inverse trig functions have a certain domain and a certain range. Well, if you shift things left and right or up and down, you might change that. Okay? And that's what I want to know how to figure out. What is A going to do? How does that move my graph? Yep. Yep, that's your horizontal shift. How about B? That's your horizontal stretch. Okay, we've written this at least 7 or 8 times by now.
Pretty
What about C?
vertical stretch.
That's a vertical stretch.
And D is vertical shift.
And D is a vertical shift.
Yeah, this is like really far ahead.
Yeah, well, that's good. That's what I'm
Yeah,
hoping.
that's good.
So if you're doing horizontal stuff, that's this one or this one. What does horizontal affect? Domain or range? Domain. Domain is left and right. If you're doing vertical stuff, what does vertical affect? Range. Range is the y-axis. That's up and down. So if I ask you for the new domain of a trig function, all you have to focus on is horizontal stuff. If I ask you for the range, you focus on vertical stuff. Right? So I'm just going to show you how you find the domain and range if you transform it. Okay, that's how you find the domain of an inverse trig function. We create a compound inequality. You put the argument in the middle. Right, so I'll scroll down so you can see a problem that has an argument in it, and then I'll come back up. That's the argument. Okay, so I'll do this one as we go. Create a compound inequality, and I'm going to put it back up, so you don't have to copy it right yet. I'm going to put the argument in the middle, and it says put the original domain on the left and on the right. So what I'm going to do is I'm going to look at inverse sine. Okay, now I have to remember what the original domain of inverse sine is. If I don't, I can go back and look it up.
So negative 1, right?
The original domain is -1 to +1. Right, so it says to take those two numbers and put them on the left and the right. Okay, and why did I put equal to? Does the domain actually reach -1? Did I have a bracket on -1 or did I have a parenthesis? I had a bracket. That's why I put equal to. If it was a parenthesis, I would just put that because it doesn't equal. Right? So create a compound inequality. I just did that. And now solve it. And that's the domain. So how would you solve that inequality and get x by itself?
You could just take the sine, plug it into that formula, right?
So we're just solving this. This is what you're solving.
Yeah.
We want to get x by itself.
Oh. By 2.
Yeah, divide by 2. Where else?
Everywhere.
Everywhere, yeah. And now it says my domain is between -1/2 and 1/2. Because what this 2 does is it's a horizontal compression. Right? It's a horizontal. Bigger numbers make it smaller, and it's the opposite. So if you compress your domain by a factor of 2, it's not -1 to 1, it's now -1/2 to 1/2. Okay? Or if you don't want to write it this way, you could do it with brackets. That's the same thing. Both of these would be acceptable. So any question on how I got the domain there? Just put that in the middle and put the original domain on the left and on the right, and then solve it. Right, so that's the domain. And now to find the range, you just have to take into account the 2 things that I mentioned that are vertical: stretches and shifts. And take them into account in that order. So just to use simple numbers, if you had a range that went from, let's say, -2 to 2, and you tripled it, what would you be between for numbers if you tripled your range? It wouldn't be -2 to 2. Yeah, it would be -6 to 6. That's how you take into account a vertical stretch. And then, let's say instead of stretching, I shifted this up 1. So
It'd be -7 to negative, or it'd be -7 to 5. Or wait, no.
just the original. Like if you had -2 to 2 and you shifted it up 1,
It'd be -1 to 3.
it would be -1 to 3.
Yeah, I messed up.
Okay. That's all you have to do to take into account a vertical stretch or shift. And if you do both, take them into account in that order. That one first, that one second. Okay. Is there any vertical stretch in this problem? No, I'd have to have a number in front. Is there a plus or a minus at the end? No. So the range for this one
Just,
is the original. It's -π/2 to π/2. Okay. No change. All right. Let's look at this one. First of all, how many transformations are there here? Just one. So either the domain is affected or the range is affected, only one of them. What is this 1/3? It's a horizontal stretch or compression. Okay, so in this case, the range is not changing again. So the range we could write down right now. It's the same as the range for the original sine function, inverse sine. So now, how do you find the new domain? What do you do with this 1/3 x?
multiply it by the original, like each number.
So what would you set up?
That,
With the argument in the middle.
yeah.
What goes on the left and the right? The original domain. So now, how do you get rid of a 1/3?
You multiply by the
Yeah, which is?
3.
So multiply by 3, 3, and 3. So now I get a domain that's not -1 to 1. I've actually stretched it.
-3.
-3 to 3. So that's the domain. We've done a lot with inverse sine. We'll do one more after that's not inverse sine. Okay. What's affected here? Domain or range? Yeah, just the range. This is a vertical shift. Shifting up and down does not affect left and right. Okay, that's vertical. So the domain is the original.
Yeah.
What's the original domain for inverse sine? -1 to 1. Now, what was the original range? It was -π/2 to π/2. And what have we done with it? We've
Added 2 to
We just shifted it up 2, so you can just write it like that. There's not really a nice way to do it unless you write it as a decimal. Just write plus 2 and plus 2. Like that. Any questions on that one? All right, I'm going to skip that one. All right, let's do this one. Yep, both. There's something here that's going to affect the domain and the range. So let's start with the domain. What's the original domain for inverse tangent?
Is that negative infinity?
It's negative infinity to infinity. And you can never reach it. That's why I'm using less thans. So now to get x by itself, what do you do? Divide everything by 2. So now the domain goes from negative infinity over 2 to infinity over 2. So what's the domain? It's still negative infinity to infinity. No matter how you stretch or compress something that goes on forever, it still goes on forever. Okay? So you can't ever affect the domain of inverse tangent, no matter what you do. It's always negative infinity to infinity. Just make sure you put parentheses. And what about the range? What's the original range? And do we reach that, or are those asymptotes? They're asymptotes. So I'm never reaching those, but we're not between these anymore. What have we done? Stretched it by how much? 3. We've tripled it. So now we're going to go 3 times as low and 3 times as high. Still, we're never going to reach those points because we didn't reach them to begin with.
Pretty straightforward.
Yeah. So this is really just more of describing the transformations, which we just did. The only thing I would do on this one before I describe it, what should we do with that 1/4? Distribute it. Okay, so looking at this, can somebody tell me what's the first transformation you would do?
Plus 2.
Yep, and what does the plus 2 do?
Horizontal shift.
Yep, so shift, what direction, left or right?
Left.
Right.
Right.
Let's see, plus 2, it does the opposite, so
It's left.
it's going to go left. So it's a shift left 2. What about that 1/4?
So it's actually going to get bigger, right?
Okay, if we say it that way, it's going to stretch it by how much?
Multiple of 1/4. So make it 1/4 times.
So we can either say that it's, well, it's not, you can't stretch it by 1/4. Because if you, that's like, if I stretch the number 10 by a half, it really turns into 5. It got smaller.
So then multiplying it by, well, aren't you multiplying it by the reciprocal anyway?
Yeah, so you could say it stretches by a factor of 4. That's how you could say it. Okay? It really is going to be a horizontal stretch by a factor of 4. What about the 3?
Let's say vertical stretch.
Yep, by how much?
Factor.
Vertical stretch by a factor of 3. We've done this before.
Shift it down.
And then a shift down 5. So nothing really new with any of that stuff. Okay. In fact, it doesn't matter what I put here at all. I can cross this out and just say what transformations are happening with the mystery function. Okay, it could be anything. Right, and then the last thing we've really already talked a little bit about, but it's just how to type it in on the calculator. So how do you type in inverse sine of 0.5? Second, sine, 0.5.
There you go.
And how would I write my answer?
30
30
degrees.
degrees, yes. So anytime you do inverse trig, the answer has to have a label of either degrees, or if you don't put a label, then what are you assuming? You're assuming radians. This problem, it didn't say whether to use degrees or radians. On a test, I would. But this one, you can do it any way you want. So 76.9 degrees. So those two worked out fine. What's going to happen with this one?
Sine will work.
It's not going to work, because remember what was the
Greater than 1.
domain was -1 to 1. So if you try to type that in, you're going to get an error.
So is that undefined or just no solution?
Yeah, you could say it's undefined. Can't do that one. That one you can do. But can't do C. All right, so any questions on that? All right, so that finishes up 7.2 part 1. And we're not going to get to 7.2 part 2 for quite a while, because next week is shop, the next week is midterms, then the next week is shop, and then the next week is when we'll finally get back to 7.2. So,
I'm gonna resolve
Maybe a
this.
nice review day. The next week, we're gonna have.
all right, so on, yeah, it's not due for a while. So on 394, it's 1 through 9, just the odds. 13 to 20, 22 to 24, and 27 to 32. Okay, so the next time I see you, let's see, so this will be shop. Well, I'll see you on the 17th. So this is due on the 17th.
Okay.
Okay, and then the next lesson that we learn won't be until the 30th.
Just the odds of 1 through 9.
Just the odds on 1 through 9.
June 17th, middle school. No, we have to come to school to hand it, so.
You got to come in on Martin Luther King Day to turn in your homework.
We'll celebrate.